lecture of the course Mathematical Aspects of Biomedical Electronic System Design. Today we will continue with our discussion on random variables. In today's lecture we will see a few common discrete and continuous random variables. We will see what their means and variances are. We will also see quite a few examples. So let us start with today's lecture. We will start with common discrete random variables. Let us begin with uniform random variables. Consider an experiment of randomly choosing a number. When I say randomly choosing, I mean without any bias. From the set A plus 1, A plus 2, dot B. Here A and B are two numbers. Then the chosen number has uniform distribution. That is, the probability that it will take any of these values, A plus 1, A plus 2, etc. is same. So, if when we say that X is uniform, what we mean that probability mass function of X is a constant. It doesn't depend on K. It is B minus A plus 1 for all K in A plus 1 dot B. Notice that there are total B minus A plus 1 elements in this set. So each one has probability 1 by B minus A plus 1. It's 0 otherwise. Clearly, the CDF of X can be written as Fxx equal to 0 if X is less than A. It is floor of X minus A plus 1 divided by B minus A plus 1 if X is between A and B, and it is 1 if X is greater than or equal to B. Note that the floor of a number X is the largest integer that is less than or equal to X. For instance, floor of 2.2 is 2, floor of 2.001 is 2, floor of 2.999 is also 2, but floor of 3 is 3. Next, we can see that mean of the uniform random variable can be computed using the formula that we had seen earlier. So it will be K times Pxk, K ranging from A to B, and it turns out to be A plus B by 2. Moreover, variance of X turns out to be equal to B minus A plus 1 whole square minus 1 divided by 12. Let us see an example. Suppose X is uniform over the set 1, 2, 10. Then what will be probability that X will be between 1 and 6? So probability of X lying between 1 and 6 will be I equal to 1 to 6, 1 by 10. 1 by 10 is the probability of X taking any value, any integral value. So this will simply be 6 by 10. Let us now move to the next random variable, and that is Bernoulli. Before we see Bernoulli random variables, let us consider an experiment, and this experiment will refer to again and again in today's lecture. So let me call it experiment star. Let's see what it is. It is an experiment whose outcomes can be classified as success or failure. For instance, what we mean that if this is the set of all outcomes omega, then we can divide the set of outcomes in two parts. These outcomes correspond to success and these outcomes correspond to failure. For instance, we can think of tossing a die where outcomes are 1 to 6, but we may consider odd numbers as success and even numbers as failure. So we can partition the set of outcomes in these two parts. Let's call the success 1 and failure 0. Then this kind of classification gives rise to Bernoulli random variable. So this gives rise to Bernoulli random variable or Bernoulli distribution. What is Bernoulli distribution? If X is Bernoulli P, this means the collective probability of all the outcomes that lead to success is P. So probability that X is K is P if K is 1 and it is 1 minus P if K is 0. Okay. One can easily see that mean and variance of these random variables are P and P times 1 minus P respectively. In fact, we had seen this calculation in the previous lecture. Now we look at the third random variable that we commonly see, and it's binomial. To understand binomial random variable, let us consider n repetitions of the above experiment, that is experiment star, and count the number of successes. Then the number of successes is given by binomial distribution. Okay, so when we say that X has binomial distribution with parameter P, what we mean that the probability mass function of this random variable is Px equal to kh n choose k, p raised to k, 1 minus p raised to n minus k. Here k is varying between 0 and 1. When we do n repetitions, the number of successes could be anything between 0 and k. To compute the mean of this random variable, let us observe that expected value of x will be k equals to 0 to n, k times n choose k, p raised to k, 1 minus p raised to n minus k. It can be easily seen that this summation is n times p. Similarly, variance of x can be seen to be equal to np times 1 minus p. Let's consider an example. Suppose a fair coin is tossed 10 times. So tossing a fair coin is an instance of experiment star. Here success may corresponds to a head, failure may corresponds to a tail. So fair coin is tossed 10 times. Let x denote the number of heads, b the number of heads. Then clearly from the above description, x follows a binomial distribution and probability that x will be k, some number k will be 10 choose k, half raised to k times half raised to 10 minus k. Right? Since it's fair coin, we have p equal to half, and this is for k between 0 and 10. Similarly, probability that x will be greater than or equal to 3 can be written as summation k equals to 3 to 10, 10 choose k, and the whole thing multiplied by half raised to 10. Okay. Let's consider another distribution that is quite common, and this is geometric distribution. To understand geometric distribution, let us again think of experiment star, and in fact let us think of repeated trials of experiment star until we get a success. Again, consider repeated trials of experiment star, then the number of trials until the first success this has geometric distribution is given by geometric distribution. Okay, so if x is a geometric random variable with parameter p, then its PMF is given by probability of x equal to k is 1 minus p raised to k minus 1 times p. Here k is number greater than or equal to 1. In this case, the CDF of the random variable x, fx can be written as 1 minus p x floor. We can compute the mean and variance of geometric random variables using the formula that we saw in the last lecture. So in particular, expected value of x will be k equals to 1 to infinity k times 1 minus p raised to k minus 1 times p, and it turns out to be equal to 1 by p. Similarly, variance of x turns out to be 1 minus p by p square. Let's see an example. Suppose an unfair coin with head probability p is flipped repeatedly. An unfair coin with head probability p is flipped, tossed repeatedly. Let n denote the number of flips until a head occurs. Until a head appears. Then n will be geometric random variable. Then n will have geometric p distribution. Let's see one more example of a discrete random variable that is very important, and this is Poisson. For a positive number lambda, we say that a discrete random variable x has Poisson distribution with parameter lambda if its PMF is given by the following expression: probability that x will be k is e raised to minus lambda raised to k factorial k. This was one of the random variables that we saw in the last lecture, and there we saw that expectation of Poisson random variable is lambda and its variance is also lambda. Let's see an example to illustrate Poisson random variables. If the number of accidents occurring on a highway each day, and let us call this number n, is a Poisson 3 random variable, then probability that no accident occurs in a particular day, probability that no accident occurs on a particular day, that is probability that n will be 0 according to the PMF given above, it would be e raised to minus 3, which is roughly 0.05. Similarly, probability that at least one accident occurs on a particular day, that is probability that n is greater than or equal to 1, it will be 1 minus probability that n equal to 0, so it will be 1 minus e raised to minus 3, which will be roughly 0.95. So these were a few common discrete random variables. Now we turn to common continuous random variables. We see a few of those. And the first one in our list would be again continuous uniform random variable. To understand continuous uniform random variables, let us consider an experiment of randomly choosing a number, again randomly means without any bias, from the interval AB, from the interval AB, here B is greater than A, then this chosen number has uniform continuous uniform distribution. Then the chosen number has continuous uniform distribution. So if X is uniform over AB, we have already seen that X will have a PDF that will be constant over the interval AB. We discussed this in the last lecture, and it will be 0 outside. So in fact, since the area under the PDF should be 1, this value will be 1 over B minus A. Okay, so X being uniform means its probability density function fxx will be 1 over B minus A. So this is fxx for X in AB. Here B is greater than A, it's clear from the picture, and it's 0 otherwise. Clearly, its a CDF can be written as fxx, which will be 0 if X is less than A, X minus A divided by B minus A if X is between AB, and it is 1 otherwise if X is greater than B. Okay. Moreover, its expectation is A plus B by 2, same as in the discrete case, and variance is B minus A whole square divided by 12. This has slightly different expression than in the discrete case. Let us see an example. Suppose x is uniform over the interval 0 10. Then probability that x will be between 1 and 6 will be integral from 1 to 6 integral of PDF. So PDF has value 1 by 10, 1 by b minus a, that is 1 by 10 dx. So this is again 6 minus 1 by 10, that is 5 by 10 or half. Next we see a very common distribution called exponential distribution. To understand exponential distribution, consider lifespan of an object whose remaining lifetime does not depend on its age. Lifespan of an object whose remaining lifetime does not depend on its age. Then the lifespan of this object has exponential distribution. Then the lifespan of this object has exponential distribution. For instance, suppose we have a bulb whose remaining lifetime does not depend on its age, then the lifetime of the bulb is considered to have an exponential distribution. For a number lambda greater than 0, we say that x has exponential distribution with parameter lambda if its density is lambda e raised to minus lambda x for x greater than or equal to 0, and it's 0 for all x that are negative. Since we are talking of lifespan, so it's natural that density be 0 for all the negative values of x. The CDF of exponential random variable fx is given as follows. Fx x would be 0 to x lambda e raised to minus lambda x dx, that is integral of density from 0 to x for x greater than or equal to 0, and it will be 0 for all negative values of x. It can be easily checked that CDF is 1 minus e raised to minus lambda x for all x non-negative, and it's 0 for all x that are negative. The mean of the exponential random variable x can be computed as 0 to infinity x lambda e raised to minus lambda x dx, and it turns out to be equal to 1 over lambda. Variance of exponential random variable turns out to be 1 over lambda square. There is an interesting connection between exponential and Poisson random variables. The connection is as follows. If x is exponential random variable with parameter lambda and n is number of lifespans in a duration 0 to L, then n turns out to be Poisson with parameter L by lambda. So we have a connection between Poisson and exponential random variables. The next distribution that we will see is also one very commonly encountered, and this is gamma distribution. For constants lambda and alpha that are both positive, x is said to be gamma distributed with parameters lambda and alpha if it has density lambda raised to alpha, x raised to alpha minus 1, e raised to minus lambda x divided by gamma alpha for x greater than or equal to 0 and 0 for all negative values of x. Here gamma alpha is normalizing constant, and it is given by expression 0 to infinity e raised to minus x raised to alpha minus 1 dx, and in fact this is called gamma function, called gamma function. The gamma function has a few interesting properties. For instance, gamma t plus 1 is t times gamma t for all t greater than 0. If n is a positive integer, then gamma of n turns out to be factorial n minus 1. So gamma of n is factorial n minus 1 for all n in z plus plus, that is for all positive integers. In the context of gamma distribution, the constant alpha is called the shape parameter. Alpha is called the shape parameter. The parameter lambda is called the rate parameter. And often 1 over lambda is referred to as scale parameter. The CDF of gamma distribution can be written as follows. CDF fxx, it is small gamma of alpha times lambda x divided by gamma alpha for all x greater than or equal to 0, and it is 0 for all negative values of x. Here the function small gamma alpha x is 0 to x y raised to alpha minus 1 e raised to minus y dy, and this function is called incomplete gamma function. This is called incomplete gamma function. The expression of CDF for the non-negative values of x, that is this expression, this itself is called regularized incomplete gamma function. The mean of this gamma distributed random variable expected value of x turns out to be equal to alpha over lambda. Its variance turns out to be equal to alpha over lambda square. There is a connection between gamma distribution and exponential distribution. In fact, if we consider the special case of gamma distribution where alpha is 1, this case corresponds to exponential distribution. So this corresponds to exponential lambda distribution. Note that in the above expressions of mean and variance, if I set alpha equal to 1, I get 1 over lambda and 1 by lambda square respectively, and these are precisely mean and variances for exponential lambda distributions. The next distribution that we will see is called beta distribution. As in case of gamma distribution, we consider two constants alpha and beta, both positive again. So for alpha and beta positive constants, we say that a random variable x is beta distributed with parameters alpha beta if it has density fxx, that is x raised to alpha minus 1, 1 minus x raised to beta minus 1 divided by b alpha beta for all x in 0, 1 and it's 0 otherwise. B alpha beta is a normalizing constant and it is equal to 0 to 1 x alpha minus 1, 1 minus x beta minus 1 dx, and in fact it turns out to be equal to gamma alpha times gamma beta divided by gamma of alpha plus beta Notice that here this gamma function is same gamma function that we saw in the context of gamma distributions. This b itself is called beta function. In the context of beta distribution, both these parameters alpha and beta are called shape parameters. The CDF of beta distribution fx can be written as follows. Fx is b alpha comma beta comma x divided by b alpha comma beta for x in 0 1. It is 0 for all negative values of x and 1 for all values of x greater than or equal to 1. Here the function b of alpha comma beta comma x is given by 0 to x integral 0 to x t raised to alpha minus 1 minus t raised to beta minus 1 dt, and this is called incomplete beta function. The expression of CDF for the values of x between 0 and 1, that is this expression, this itself is called regularized incomplete beta function. Expectation of the above beta distributed random variable, that is Ex, turns out to be alpha divided by alpha plus lambda, and its variance turns out to be alpha lambda divided by alpha plus lambda times alpha plus lambda plus 1. There is a connection between beta distribution and uniform distribution. That is special case of beta distribution when alpha as well as beta both are 1. This corresponds to uniform 0 1 distribution. So these were a few facts about beta distribution. We end this lecture with another very important continuous distribution, and this is Gaussian distribution, also known as normal distribution. We again consider two parameters, mu and sigma. Mu is a real number and sigma is a positive real number. We say that x is Gaussian distributed or normal distributed with parameters mu and sigma if it has probability density function fxx equal to 1 over root 2 pi sigma e raised to minus x minus mu whole square divided by 2 sigma square for all x. If we plot this PDF, it looks like a bell-shaped curve, something like this, with its peak at mu and the value of the PDF at the peak 1 over root 2 pi sigma. This normal distribution is also denoted as n mu sigma square. The cumulative distribution function of Gaussian distribution turns out to be fxx equal to half 1 plus the so-called error function of x minus mu divided by root 2 sigma for all x. Here the error function is given as ERFX equal to 2 over root pi 0 to x e raised to minus t square over 2 dt. This is called error function. The mean of the exponential random variable x described above, expected value of x, can be computed as minus infinity to infinity x 1 over root 2 pi sigma e raised to minus x minus mu whole square divided by 2 sigma square dx, and it turns out to be equal to mu. Variance of this random variable turns out to be equal to sigma square. Of special interest is the special case where mu is 0 and sigma is 1. The special Gaussian distribution with parameters 0 and 1 is called standard Gaussian distribution or standard normal distribution. Here are a couple of facts about Gaussian distributions. If x is standard Gaussian, then probability that x will take values between minus small x and plus small x, it turns out to be equal to error function of x. Further, if x is Gaussian with parameters mu and sigma square, then x minus mu divided by sigma, it turns out to be Gaussian with parameter 0, 1. That is, x minus mu by sigma is a standard Gaussian random variable. These were a few facts about Gaussian distributions, and this also brings us to the end of this lecture. Thank you.